be formed will always be rich in the low boiling point substance. Okay, in this particular case it happens to be the ammonia. Okay, so that is what I am showing here. The first vapor bubble is quite rich in ammonia vapor, ammonia this thing. So the concentration is given by zeta 1 V. V stands for vapor, as I was explained. And if you look at the point 2, where you have liquid as well as vapor. So what is the liquid phase concentration and what is the vapor phase concentration? Since both liquid and vapor are at thermal equilibrium, both will have same temperature. Okay, so T2L for example will be equal to T2V. Okay, and what you have here, you have a mixture of saturated liquid and saturated vapor. Okay, so the concentration can easily be obtained if you are drawing this temperature line, and where this line intersects the bubble point line, that will give you the concentration of liquid. Okay, and where this where this line constant temperature line intersects the dew point line, that will give you the vapor phase concentration. Okay, so by using this you can find out easily what is the concentration at different phases. So it is interesting to see that the concentration will be different in the two phase region. Okay, and once you come back to the superheated region, again you will find that because of the conservation of the mass, the concentration again remains same. Okay, so this is how once you have the charts you can find out at any point, for example at some other point, what is the concentration of the liquid, what is the concentration of vapor. Okay, at some other point, what this is the concentration of the liquid, this is the concentration of the vapor. Okay. Of course, this experiment can also be carried out in a reverse manner. That means initially you can take a superheated vapor and start cooling the vapor. Okay, so you can proceed either in this manner or in this manner. Okay, ultimately you will get the same curve. And for the two phase reason, just now I have explained, you can write the mass balance. So the total mass is always conserved, total mass is nothing but M2L plus M2V, and you can also write a conservation equation for the ammonia mass. Okay, this is nothing but the total mass of ammonia in the mixture, that is nothing but ammonia in liquid phase plus ammonia in vapor phase. Okay, so you can write these two equations from the mass balance. Okay, and from these two equations you can easily show that you can eliminate M1, and you can easily show that M2 liquid by M2 vapor is nothing but zeta 2V minus zeta 1 divided by zeta 1 minus zeta 2L. Okay, or you can also write this in this form. Okay, this particular rule is called as mixing rule, or it sometimes it is also called as lever rule. What do you mean by lever rule? Lever rule means this point actually acts as a fulcrum. Okay, so for example, we want to find out what is the mass of this thing. Okay, the total mass into this distance will always be equal to mass of vapor into this distance. Okay, so as this distance increases, you will find that this point moves closer to this dew point line, that means vapor concentration increases. Similarly, when this point moves this side, you will find that liquid concentration increases. Okay, so that is what is shown in this equation. Of course, if you have carrying out this experiment at two different pressures, let us say, then you will get two different lines. Okay, this is for one pressure P2 and this is for another pressure P1, and P2 is greater than P1. So the same thing can be repeated at different pressures. So at different pressures you will get different lines like this. Okay, right. So this is a typical bubble and dew point chart for a binary mixer. Okay. So now let us look at enthalpy of ammonia water mixers. First let us look at liquid phase enthalpy. Since strong ammonia water solution deviates from ideal solution behavior, the liquid phase enthalpy has to be obtained by this equation, that is H is zeta HA plus 1 minus zeta HW plus delta H mix. Delta H mix is negative because the mixing process is an exothermic process, just like water lithium bromide system. And the specific enthalpy at any concentration and temperature can be calculated from the above expression, provided we know the heat of mixing. Heat of mixing is normally obtained from measurements. Now, enthalpy charts for solution are plotted as a field of isotherms against mass fraction. In fact, I will show you the typical enthalpy chart for ammonia water mixer in the next class. So, normally they are plotted against mass fraction for different isotherms, and since pressure does not have a significant effect on liquid enthalpy except at critical point, normally the pressure lines are not shown on typical solution enthalpy charts. Okay, that means in the for the liquid enthalpy only the temperatures and concentrations are given. Okay, pressures are not normally shown, and it is also generally assumed that enthalpy of subcooled liquid is equal to the saturated enthalpy at that temperature. Okay, if you are assuming this, it will considerably simplify the calculation procedure, and it does not give really a big error. Okay, so it is a standard procedure. Now, enthalpy of liquid phase is relatively easy. So, how do we calculate the enthalpy of vapor phase? The complication comes because in the vapor phase we have both ammonia as well as water vapor. Okay. So, and the vapor enthalpy, as you know, depends upon temperature and pressure. Okay. So, to simplify the problem, again what is generally done is it is assumed that ammonia and water vapor mix without any heat of mixing. Okay, that means there is no change of phase or any chemical reaction when vapors of ammonia and water mix. Okay, in such case the enthalpy of mixer phase is given by the simple equation HV is equal to zeta V HAV plus 1 minus zeta V HWV, where zeta V, as you know, is the vapor phase mass fraction, and HAV and HWV are vapor phase enthalpies of pure ammonia and pure water vapor. Now, the problem comes because HA and HW for vapor phase are functions of both pressure and temperature. Okay. So, an approximate but practically useful method is to evaluate the vapor enthalpies of ammonia and water at pressures Pa and Pw given by Pa is equal to Y into P total and Pw is equal to 1 minus Y into P total. Remember that this is an approximate method, but it gives reasonably accurate results. And what is Y here? Y is the vapor phase mole fraction of ammonia and P total is the total pressure. If ammonia and water vapor behave as ideal gas, you will find that Y into P total is nothing but the partial pressure of ammonia in the mixer. Similarly, 1 minus Y into P total is the partial pressure of water vapor in the mixer, but you will find that most of the times the mixer deviates from ideal gas mixers. So, Y into P total and 1 minus Y into P total do not give partial pressures. Okay. Now, let us look at enthalpy composition diagram. Charts of enthalpy, temperature, mass fraction are available, which give both liquid as well as vapor enthalpy of mixers. As I said, I will show this in the next class. But right now what I will show is enthalpy composition diagram at a single pressure, because in order to understand it is easier to start with a single pressure. At a single pressure, the isotherms in two phase region are obtained by joining saturated liquid and vapor state. So, let me show the enthalpy saturation diagram, enthalpy composition diagram at single pressure. Okay. So, what we have here is the composition of ammonia in as y axis and enthalpy, I am sorry, in x axis, and enthalpy on y axis. Okay. So, again you have the bubble point line and the dew point line. In addition to that, in order to find the enthalpy of vapor and composition of vapor, an auxiliary line is shown. Okay. So, this line is an auxiliary line. Okay. And remember that this is for a single pressure, that means at a constant pressure. And the isotherms are shown in the subcooled liquid region. This is the subcooled, remember that this is subcooled liquid for this pressure. Okay. So, the isotherms are shown in the subcooled region, and this is the one typical isotherm T. Okay. So, this isotherm intersects this bubble point line at this point. Okay. So, let us assume that initially we have a saturated liquid at this point. So, it has a liquid phase mass fraction of zeta L. Okay. I would like to find out what is the mass fraction of the vapor that is in equilibrium with this solution. So, in order to find that, and what is its enthalpy. So, in order to find that, what normally is done is you draw a vertical line starting from this point and find the point that is the intersection point between the auxiliary line and this vertical line, that means this point. Okay. So, draw a vertical line and get this intersection point. From this intersection point, draw a horizontal line. where this horizontal line intersects the dew point line, that will give you the vapor phase mass fraction. Okay. So, once you get this point, the vapor phase mass fraction is obtained by going down vertically, and this is the vapor phase mass fraction, and this is the enthalpy of the vapor phase, saturated vapor. Okay. Similarly, this is the enthalpy of the saturated liquid. What it means is at this particular condition, saturated vapor of this mass fraction and this enthalpy is in equilibrium with saturated liquid of this mass fraction and this enthalpy. Okay. So, that is how you have to find out the saturated vapor enthalpies and mass fractions. And you can see that here I am varying the concentration from 0 to 1, that means from pure water to pure ammonia. So, obviously this difference, which is nothing but the enthalpy difference between saturated liquid and saturated vapor, is nothing but your latent heat of vaporization for pure water at this pressure. Similarly, at the other end, the difference, this difference or this distance gives you the latent heat of vaporization for ammonia at this particular pressure. Okay. And the line joining this point, okay, so for this pressure, the line joining the saturated liquid point with the saturated vapor point, that means this line is the isotherm. Okay. That means the isotherm T is like this. Okay. Right. And point B, what is point B? Point B is in the two phase region. So, this is the two phase region. So, if you look at point B is in two phase region, and at this point the temperatures are all equal, that means Ta is equal to Tb is equal to Ta dash. Okay. And at this two phase this is the enthalpy of the two phase mixer, I am sorry, this is the mass fraction of the two phase mixer, and this is the enthalpy of the two phase mixer. Okay. So, this is a very useful chart, and if it is if you plot this for different pressures, as you will see later, you will have different lines. Okay. Different bubble point lines, similarly different dew point lines, and the different auxiliary lines. Okay. So, you will find a whole lot of lines on a typical total enthalpy composition diagram for a binary mixer. And as I said, an auxiliary line is used to find the saturated vapor state and its enthalpy from saturated liquid state. For points lying inside the two phase region, the specific enthalpy Hb has to be obtained from the sequence, just like a two phase mixer of any fluid. Hb is equal to 1 minus the psi b into Hl plus psi b into Hv, where psi b is the quality or dryness fraction, and Hl and Hv are the saturated liquid enthalpy and saturated vapor enthalpy. Okay. And the dryness fraction is given by again what is the mass fraction at that point minus saturated liquid mass fraction divided by the saturated vapor fraction minus saturated liquid fraction. Okay. In actual enthalpy concentration diagrams, the isotherms are not shown in two phase region because for each set of pressures you have a set of isotherms in the two phase region. Okay. So, it becomes very confusing. So, normally in enthalpy composition diagrams, isotherms are not shown in the two phase region. If that is the case, how do we find the temperature in the two phase region? Okay. That I will discuss little later, and also it is not possible to fix the state of the mixer just from temperature and mass fraction alone, because one can calculate enthalpy of the mixer from temperature and concentration, but you cannot say whether it is in superheated region or subcooled region or saturated region or two phase region just by knowing temperature and composition. Okay. For example, a liquid mixer with a mass fraction of 0.4 and a temperature of 80 degrees will have an enthalpy of 210 kilojoule per kg. Okay. This you can obtain from your enthalpy composition diagram, but it will be in subcooled condition if the pressure is 4.29 bar and saturated condition if the pressure is 8.75 bar. Okay. So, depending upon the pressure for the same composition and temperature solution can be in any state. Okay. So, to remove the ambiguity you have to specify the pressure so that you can completely fix the state. Okay. Determination of temperature of mixer in two phase region, I was mentioning that you have to do how do we decide this. Normally a trial and error method has to be used to determine the temperature, and you have two methods, one is graphical, other one is numerical. So, let me quickly explain this. Okay. So, in the graphical method, let us say that point x is the point in two phase region, and I would like to find out what is the temperature of the mixer at this point. Initially what we do is, we know that for this point I know that this is the mass fraction and this is the enthalpy. So, I know the mass fraction and enthalpy of the two phase mixer, but I do not know its temperature. Okay. So, to start with, what you do is you draw a vertical line in this manner, and the point where it intersects this auxiliary line, remember that this is auxiliary line, this is your dew point line, and this is your bubble point line. Okay. So, where this vertical line intersects the auxiliary line, that is point A double dash, you draw another horizontal line. Okay. This horizontal line intersects the dew point at A dash. Okay. Now, what you do is you draw a straight line passing through A dash and x. Okay. That is this line. Okay. So, this line intersects the bubble point line at point A, right. So, now what we have to do is you draw another vertical line from point A, and where it intersects again the auxiliary line, the point is B double dash, and from here you draw a horizontal line, and this horizontal line intersects the dew point temperature at point B dash. Okay. So, again draw one straight line passing through B dash and x, and this intersects the bubble point line at x. Okay. So, to repeat the process, what you have to do is you have to draw again a vertical line from this intersection point, to draw another horizontal line, get this point, from this point again you draw line passing through x. So, you get one more set of points. So, this process has to be continued till the points here and points here converge. Normally the convergence takes place within 3-4 iterations. Okay. So, this is the graphical trial and error method for finding the temperature. So, how do you find the temperature from this method? Once you know the finally you know that this is, let us say that this is the line, the converged line, that means this is the line which gives the isotherm, because you know that at this point is an equilibrium mixture consisting of saturated vapor and saturated liquid. Okay. That means this one has got to be the equilibrium line, and the temperature in the subcooled region which meets this point has to be the temperature of the two phase mixer also. Okay. So, you have to read this temperature. So, this temperature is same as this temperature. Okay. So, this is the procedure, and numerically the temperature can be obtained from the equation which needs to be satisfied for each end of the isotherm passing through x. Okay. That means the isotherm passing through the two phase mixer has to satisfy this equation. Okay. Where Hv and Hl, as you know, are saturated vapor and liquid enthalpies. Similarly, zeta V and zeta L are saturated vapor and liquid compositions, and Hx and zeta x are the mixer properties, and we know these mixer properties. Okay. So, these things are known to us. So, what we do is initially you assume a guess value of Hl and zeta L, then from the guess value find out Hv and zeta V from your Ht composition chart. Okay. Then you substitute these values in this expression, and substituting this you find this value and this value. Okay. And again use these two values to find again new values of Hv and zeta V. So, this procedure has to be continued till you get again converse values. Now, let us quickly look at some basic steady flow processes with binary mixers. First very simple process, that is the adiabatic mixing of two streams. So, let me show this process. So, what we have here is an adiabatic mixing chamber, that means there is neither heat transfer to or from the mixing chamber, and in this mixing chamber two streams, one stream at condition 1 and the other stream at condition 2, they are getting mixed in this adiabatic chamber, and finally what you are getting out is a single stream at state 3. Okay. The same thing is shown on enthalpy and composition plot. So, this is the state 1, this is the stream 1, and this is the